All right. Welcome again, Friday MedChem. Um, so a few announcements before we get going. I wanted to map out what Monday is going to look like heading into your exam. So it's going to be held both in person and on Zoom. What I would say is, so I guess to start on the Zoom end of things, I will be posting the exam 15 minutes ahead of time as a module. I'm going to say exam one. Um, when you head to your Canvas to go get that, I expect you at that point to then be on Zoom, and from that point forward, you're on. Your camera's got to be on. I got to see that you're not doing something or hanging out with friends. Um, in class, um, or actually, sort of back to the Zoom folks. I would expect that you just put your name on it, flip it over, or whatever you got to do to not be looking at it. You're not to look at it until 10:10. Okay. In person, you guys are going to come in, grab a copy, and head back to your respective locations and write your name on it, flip it over, and wait patiently until we get started at 10:10. We will promptly be starting at 10:10. A piece of advice heading in is this exam moves very quickly. So make sure that you're not late. That's not a good strategy. I promise every minute is worth the time. The other thing is for the folks that usually like buzz through the exam and then like bolt, I would say really use the 50 minutes to your advantage. It's most like, I would say definitely read carefully, right? All the directions. There's going to be, you get some people just leave points right on the board just by not reading the directions. Let me see. Oh, for folks that do require extra time, I likely know that already. You should either be taking it in sort of one of the places that we've sort of assigned, or taking it over Zoom. Usually, what I would do is have you take it in person if we weren't backed up against another class after, but we are. So make sure that you are taking it on Zoom. If you have any questions about that, and you are one of those individuals, please reach out to me, and we can get things arranged. Um, let's see. Items you can bring into the exam are going to be a pencil, a pen. You probably should do your. I would say actually definitely do your exam in pen, just so it's so it's permanently on there, right? I'll also allow you to use a blank sheet of paper for those that are going to do it in person. I'll have blank sheets of paper here. For those of you at home or on elsewhere on Zoom, just before the exam, I want you to show me if you're going to use paper that it's blank. And then the other thing that's come up is a model kit. You guys want to bring a model kit, that's fine, with the exception of having a model already built of something. So I want you to come in fresh with a model kit that has nothing built. So Abesh and I will both be in here, and we'll be monitoring both the Zoom call as well as what's happening in here. Once I'm gonna basically right at 11. I'm gonna tell you guys to drop your pens and pencils, etc., and be done. Please don't continue to work after that. I know that sounds simple, but we've had that problem before. Some sort of advice heading into the exam, guys. Answer all the questions. Definitely answer all the questions. I think I mentioned this on several different recordings now. Definitely make sure that you at least go after some of the points. I'm not gonna dock you for, or actually at least you get at least a chance of getting some points when you answer it right. The other thing I would say is don't get too, and this is, we had this discussion actually in one of the reviews, don't get too wordy with your answers. Use, you can use, pictures, right? If you want to draw those, or you can use sort of just bullet points that sort of get your point across. Sometimes people, they'll say the right answer and then they'll sort of like continue on and talk themselves out of that answer. And I'll also be looking for that. Don't just write everything that you can think of, right, that comes to your brain. So just, I would do it sort of pretty succinctly, or trying to answer them, efficiently. You're also not going to have time to write paragraphs. Okay. The other strategy, you mentioned this before, is I think it'd be worth the first 3 to 5 minutes just going through, looking at the directions, underlining, highlighting whatever you need to do to pay attention to those key aspects. The problems that gave you for practice are pretty close to the type of problems that you're going to get sort of in the shorter answer section. I would say the last question certainly is difficult, but I would say out of, I think, the 25 or 30 points it's worth, 15 to 20 of them are pretty attainable, sort of based on what I've seen sort of with studying so far. There's sort of a leap question that you'll also have. So are there any general questions? Anything I didn't cover? Abesh will be doing a review today from 2 to 5 on Zoom. I'll have a Zoom link out. I think he also is doing office hours today from I think noon to 1. So if you guys have any questions, I'll also try to pop in there for a few minutes to see how everything's going. If you guys want to ask me a question directly, it's fine. How many of you guys are planning on going to Abesh's thing? Some people, if you guys have been to 2 reviews with me, it's probably about enough. I would estimate, but feel free to continue studying. If you guys have any questions over the weekend, start discussions. I won't be able to field 1,000 emails over the weekend. Okay, so just start them in the discussion, and you guys discuss them amongst yourselves. I'll also chime in. I'll have that on the whole weekend, even on my phone. Cool. All right. I wish you all the best of luck in studying. I think you guys are going to do well. Today should be a little bit shorter of a class. I'm going to take you guys through just sort of that 3.5 lecture. I want to take a minute. Now that you guys have been through sort of the phase 1 material, I wanted to, this phase 1 metabolism, I wanted to just bring up a little bit about sort of, I guess, the organic chemistry of MedChem and sort of the arrow pushing that I think would benefit you in sort of getting familiar with rationalizing things via arrow pushing mechanisms. Again, a lot of the rationalizations that you're going to make as you go through the remainder of the course, especially after you've leaped over the exam 1 hurdle, will be rationalized by sort of knowing what an enzyme does to a molecule. For example, those hydroxylations like we talked about with P450s. And then in the event that there's some rationalizations to why the molecule turned into what it turned into, you might have to do just a little bit of arrow pushing. But I promise you, it's really only a small subset that you rely on, but you apply them across the board, and you guys will get familiar with that. And so I'll get this thing into full screen mode. So a few suggestions. So this is sort of a mix. I think, first I want to give you a few resources that you might tap into that sort of help sort of in the sort of arrow pushing arena. And so these are a little more tailored to if you're really interested in organic chemistry and you want to continue on into MedChem, but they're also will be have nice references actually to some of the material that we'll talk about in a few slides. So the first one is SYN Archive. So if you were to, there's a nice website you can go to that sort of provides a lot of arrow pushing for a lot of the sort of the reaction mechanisms that I'll show you shortly. So if you want to learn a little bit about how the aldol works, for example, there's a really nice page on that, and I'll explain that a little bit. Organic Chemistry Portal is another location that sort of is pretty intensive on the intensive in a good way on showing you sort of how arrow pushing occurs for certain reactions. This one's a little more tailored for individuals that may be interested in going into the area. I just want to provide these just in case anyone, med chem sparks your interest and you want to dive into the organic chemistry arena. These are all, I would say high level type practice problems in synthetic organic chemistry. So maybe not as important to med chem. The art of writing reasonable organic reaction mechanisms. I'll post this actually on our Canvas site. It sort of teaches you sort of the basic lessons in arrow pushing in general. And actually, if you just read even the first like chapter or two, that usually provides you sort of the foundation, a really nice foundation, heading into some of the arrow pushing that we'll do in here. Finally, if you're going to really dive in to the area of organic chemistry in particular, this is I would say that arguably the best reference you could have. It really goes through this is sort of strategic applications of named reactions and organic synthesis. It goes into I would say excruciating detail of reaction mechanisms, and this is another one I'll make available to you guys on Canvas. But I strongly discourage you from sharing that outside of our Canvas site. That should be, I hope, well known. None of that stuff goes out to anyone but you guys. The final one is ChemStation. I would say this is another sort of general one that you guys can tap into. When I give you this sort of whole list of them, I would say, find the one that sort of tailors pretty well to you. They all have the same type of content, but at least it'll sort of provide you another perspective about some of the arrow pushing that we'll talk about. So, what I did a bit ago, and I think this has turned out to be really useful for med chem students in the past, is put together sort of a list of mechanisms that you may or may not have heard of when you were in sophomore organic, but it also provides you sort of the arrow pushing mechanisms, ones that are really tailored to what's going to happen when a drug is going through the body, right? So we're going to talk a lot about sort of metabolism, and a lot of that comes down to once you get the drug into water, right? It's prone to, for example, hydrolysis or acid base type chemistry. You probably can appreciate that, right? As the drug enters more acidic or more basic environments, it's going to sort of come into some of these types of mechanisms are going to come into play. So I think I would not get hung up so much on like the names of the reactions. I think a lot of people do that, and don't do that. So just look at sort of the fundamentals of what's happening. You guys are going to hear tetrahedral intermediate 1,000 times this semester. If you guys watch the reviews, we probably said that 20 times in that thing. So it'll come up all the time. And so I wanted to walk through each of these with you, just kind of give you a feel and a couple things to, I just want to point out a couple things. The first one would be sort of this Fischer esterification. Okay, and so it's important do you guys remember, was this something that was talked about in sophomore organic? It was a little bit, right? Okay. So what happens in this is you go from a carboxylic acid to an ester, and that's acid or could be base mediated. Okay, and so typically this is shown as an acid mediated process. So in order for you to have let's say your alcohol, your attack, your carbonyl, you have to protonate, you have to activate, right? That carbonyl for attack. This shows you conveniently, right, if you draw the resonance structure, where the most electrophilic site is going to be. If you sort of satisfy the positive charge of that oxygen on the left. And so that allows for attack then of your alcohol, right? And then at that point, you've now reached the tetrahedral intermediate. And then it's important to note that if you have on a carbon, if you have multiple heteroatoms that are attached to that carbon, so for example, at least in the tetrahedral intermediate, right, that's not going to be a stable structure, right? So probably what you've learned in the past, right, is you have this is a tautomerism here. That's not to be confused with tautomerism. So this is, so when they say this, what's happening is and the H atom's being transferred. This is a hydrogen transfer. Okay, so just another one of the oxygens grabs onto the hydrogen that's adjacent to it. And then this sort of tetrahedral intermediate falls apart, right? And you remove water, and you ultimately, after that, have a deprotonation by water, and then you end up with the corresponding ester, right? This is a very common thing that's going to happen throughout the rest of the course. Ester hydrolysis is exactly the opposite, right? So you start with the ester, right? This was your R in the previous reaction. And sort of in a base catalyzed process where you have OH, so OH would come from water in the body, for example. You once again, you generate sort of this tetrahedral intermediate. Right now you have an O minus, and that's going to come down and make the methoxy leave in this case. Right, so it's essentially the reverse process, right? All these things are in equilibrium. Okay, very similar, right? This one maps a little bit better onto the last one, the one from the previous slide, right? You have activation again, right? You're going to have water attack, generate ultimately the tetrahedral intermediate, and then that's going to fall apart to give you the corresponding acid. One thing I'll tell you is, I know back in the day, I think I hear a lot from people that took organic chemistry, and they say, okay, I used to go through and I used to memorize all the mechanisms, and then or memorize all the reactions we learned or mechanisms, and then go from there. It's really important sort of to take the time earlier now as you start to get thinking about exam 2 to really go through these. What I would say is put the sort of general scheme at the top of a piece of paper, and then write these out and sort of rationalize why you're doing things. It'll be really, really meaningful for you. And if you guys can nail down sort of the ones that are in here, it'll be, the rest of the course will be probably cake for you, I think. The next one, again, you guys are going to see something very similar. So transesterification. So that takes, let's say, like a methyl ester to an ethyl ester, for example. Okay, so it's, again, you're going to have very similar type of processes. And just to take you down to the acid catalyzed one, right? Again, you have activation of the carbonyl, and then another alcohol comes in, and it goes through the same process. That adds, you get to the tetrahedral intermediate, you get a proton transfer, and that helps the other alcohol leave. Okay. What is that governed by? Does anyone know what that's governed by? What's the driving force for that? It starts with an L. That might even be taking you back to the earlier days. Le Chatelier's principle. You guys remember that stuff? I know, blast from the past. Yeah, so you guys can see, right? This course brings everything together. Super cool. But anyway, right, it's a very similar mechanism, right? It doesn't matter for the last 3 type of reactions. We're not that creative in organic chemistry. right? We rely on all the same stuff. Yeah, big fundamental one, right? You guys are going to have to deal with a lot with amines in your drugs, right? And so something to keep in mind is that you're going to have to handle a little bit of amine, well, let's say enamine type formation. Are you guys familiar? You guys remember enamines? Jogging your mind a little bit. Okay. And again, this all sort of sits in equilibrium with each other. So just to walk you through that, right? All these things, right before you're going to start with attack of the carbonyl, you're going to have an activation process. Okay. That's going to, right, that's showing you sort of that resonance structure, right? To show you that this is going to be the electrophile here. Your amine is going to add, and you're going to generate what would be sort of an aminol. So that's amine alcohol. Okay. And then you get the proton transfer, right? It's looking very similar, right? This is tetrahedral intermediate again, right? It never stops. That thing never goes away. Okay. And then at this point, the nitrogen can bring its electrons down, remove water, and you generate an iminium ion. Okay. Again, right, it's showing you if that thing's going to be attacked, right? It'll be in this position here. And then in order to get to the enamine, you do a deprotonation and bring electrons up to the nitrogen to satisfy that positive charge. And then you're left with the enamine seen here, right? So what is this thing? You know, I think it's important to keep in mind that that's just an enolate in disguise, right? In fact, I would prove that to yourself by drawing that, and then draw an enolate or an enol, right? Does the same thing, right? When this thing goes, if it comes in the presence of an electrophile, the nitrogen will bring its electrons down, just like the alcohol would, right? And these electrons go and attack an electrophile. This comes straight out of some sophomore organic notes right online. So E1 mechanisms and E2 mechanisms are going to be important. So in these E1 type mechanisms, keep in mind, right? If you have, for example, a tertiary alcohol or tertiary halide, you guys are likely going to see tertiary alcohols, not the tertiary halides. What you can have is formation of a carbocation, right? Those tertiary carbocations are stable. You guys remember, usually if you guys take information out of sophomore organic, for some reason, that's the one everyone's got, right? Tertiary carbocation, super stable. Okay. So if you come in the presence of acid and you're a tertiary alcohol, it's likely that you could form, let's say, the carbocation. It's important to note then at that point that tertiary carbocation is electrophilic for one, or it can go through sort of this elimination type of process, and that sort of that E1 type of elimination. Now, for the same process to occur in basic media, right, you need a base that's going to take off the adjacent hydrogen to ultimately eliminate. In this case, it's the bromide. You're likely not going to come across E2 mechanisms that often. They're likely mostly going to go through E1 in the body. This one's here strictly to, don't freak out when you look at this thing. This happened often. Okay, so this is a great reaction. It's Osmotowicz reaction. Doesn't matter that it is that, but it's a great arrow pushing mechanism. Just so you guys can take a minute and rationalize how things are working step to step. You're not going to have something this difficult on an exam. There's no way. I would save this for a course I'm teaching next semester. Okay. But we can get into that later. Aldol addition, right? It's all related, right? So now you have this process, right, in which you start with a ketone. Again, that typically gets activated by an acid. And then you get enol formation, right? These are tautomers of each other, right? That tautomerization comes into play. So if you guys watch the videos again, you guys point out what are the key sort of elementary steps that you need to know for each of these processes. But this is exactly what I was talking about, right? That enamine can do this as well as these enols, right? It can then attack sort of another activated carbonyl compound. Okay, and ultimately, right, when you do the aldol, you end up forming sort of these beta hydroxy ketones. If you heat that up, it goes through what would be the full-blown aldol addition condensation process where you get elimination, because again you have an acidic proton right next to that ketone, and that can cause sort of what would be the E2 type of mechanism in that case, right? Ultimately to generate the alkene. Now, Baeyer-Villiger. Actually, this is one that I'm not sure. Do you guys see this in sophomore organic? It pains me. Okay. Yeah, you know what? This is happening. I got to tell them. You got to teach it. This is super important. But anyway, so this is not. It's not really working off of too much of a different principles that you've looked at from before. But the reason why this one's important really is that sort of a lot of the enzymes that you encounter are able to do this, and so some of those monooxygenases that are not P450s, and we'll talk about that in more detail in another class. But ultimately, what happens is, again, right, you get activation of your carbonyl, and then this species becomes the nucleophile. Okay, then you get to the tetrahedral intermediate. Okay, and okay, where this goes a little nuts, and this is gonna give you like heart palpitations. But what happens is the electrons then come back down, like you've seen from before, but then you actually have a migration of your R group, which releases a good leaving group in this sort of benzoic acid. You're likely not going to be faced with this one, but I would say that there could be a time it comes up a little later in med chem. So you probably do want to start to digest this a little bit. This is one of the more difficult ones you'll see. Benzoin condensation, you're likely not gonna see in the course, but I did want to give it to you because it functions off of a lot of the same principles. You have, this is, first of all, it's not a base, but it's a good nucleophile. Okay, and it attacks, for example, a carbonyl compound, and then that cyano is an electron withdrawing group. So very similar to like the aldol type of condensation, right? You're able to form an anion right here. Okay, sort of generates sort of a pseudo-enolate, and then it attacks another carbonyl compound. So that's just one. If you want to get just a little more practice, sort of rationalizing why you're pushing arrows, it's a really good one. Claisen, right, is very similar. This is probably another one that you guys saw. Is that true? Yeah, some head nods. Okay, that's good. Again, right, you form the enolate, right? Keep in mind, right, in this case, right, you have, in the case that it's acid promoted, right, you have activation of the carbonyl, but in the case that it's base promoted, right, you could directly do the deprotonation and generate, for example, the enolate. So, for example, right, they generate the enolate here in the base promoted process, right, and then that can attack another ester, right, and again, you go through the tetrahedral intermediate, electrons come down, and you lose a leaving group. All very similar. Friedel-Crafts, do you guys go through that? Yeah. Okay. Not particularly important in medicinal chemistry, but I would say it does come up every now and then. I'm not sure if we'll cover an example. We might a little later. Yeah, right, this is another example of Friedel-Crafts, right? Friedel-Crafts acylation and alkylation. Right. this is, you know, if you like have been anywhere like on campus and someone knows me, I can tell you that my goal is that the entire campus knows the manic reaction. And the reason why is because it has the flavor of everything that we just talked about all in one. If you can arrow push in the manic reaction, you're golden. Okay. And here's why, right? You get condensation of that amine onto a carbonyl compound, right? We talked about that. But then on top of that, it's coupled, right, with an aldol reaction. Right. So you generate the enol, and that attacks actually the iminium. Right. It's like all in one. So if there's one thing you study and want to really get it down, it would be the manic reaction. This is such an important reaction, and not because I'm a synthetic organic chemist, but because it is so important in your training in med chem. Super, super cool. In fact, it's like, oh, I can't say enough. The other thing I wanted to show you, and this is in sort of in the context of the Betty reaction. I know you guys, again, you guys are getting a bunch of named reactions today. Forget the names. Just put a piece of tape over each of those names. You don't have to. I just put it there for reference. But the Betty reaction is awesome because, again, right, it puts together everything. Okay, so you have the amine condensed onto the aldehyde, and then you have this. I know you guys look at maybe this phenol and you're like, well, what in the world would you do with that? That's just a disguised enolate. Look, it's drawn right here, enol. Isn't that sweet? It's so cool. Like, think about how many named reactions you guys are going to crush it out there. You know what I'm saying? Okay. But again, right, it goes to the very same thing, right? It gets activated. The carbonyl gets activated. Amine comes in. You generate ultimately iminium, right? And then you have, here it is. It's like an aromatic type of manic reaction. Super cool. That MCPBA comes in again, sort of not in the context of a Baeyer-Villiger react. Did you guys learn epoxidation? Yeah, they did, and they didn't teach you the other one. You guys learned this? How can you guys all nod? Is that true? Okay. All right. Cool. Well, I'm happy that you've seen this at least, right? This is exactly what the enzymes are doing, right? They do it enzymatically. So it's important that you know this more or less, just sort of to gain appreciation for sort of what the enzymes are doing when they are able to generate the epoxides. Fischer-Indole synthesis, I would say this is maybe too high of a level of something. But what I do want you to notice is that, again, it's very similar to sort of the manic reaction, right? In that you have sort of this condensation of an amine, right? Ultimately, you have a formation of an aminium ion, or sorry, an enamine rather, right? That's ultimately able to add into the aromatic. This is not particularly important that you know this one, but if you want to go like next level in like really making sure that you have your skills polished, this is a real good one to practice. And we can talk about that as we get closer to like exam 2. Robinson annulation is another one, very similar. Okay, so this one brings in sort of this, we talked about this in a review session, actually, in sort of these alpha beta unsaturated carbonyl compounds, right? The most electrophilic position of those is not in sort of this, what they call, if you just count with me, 1, 2, 3, 4, you guys usually think of the 2 position being the most electrophilic site. But if you draw the resonance structure, which I'll refer to the second review session for, who covered this, the most electrophilic site ends up being the 4 position after you draw the resonance structure. Okay, but again, this all operates the same way, right? You have the enolate formation, okay, and now your electrophile is now just the the alpha beta unsaturated ketone. Once you get there, right, you ultimately get to this intermediate that's on the top right, and it all happens again, right? It just does an aldol condensation and shuts the whole thing shut. I mean, that's really neat. SN2. I know. As you guys get overwhelmed, I give you the easiest one. I feel you. I feel that's cool. It's I'm all about. Yeah, there's this thing. Another type of reaction. It's the Henry reaction. You guys are going to see nitro groups on some of these molecules. It's important to note that the hydrogens right next to the nitro group are really acidic, right? So those can generate what would be sort of the corresponding nitro version of an enolate. It's called a nitronate. We're not that clever. Anyway, once you generate the nitronate, which is seen here, that can then attack a carbonyl compound, right? Very similar to the aldol, and then get protonated, and you end up with sort of the beta hydroxy compound. These arrows are beautiful. And the reason why they're beautiful is this came right from the Wikipedia page in which I wrote. Yeah, that's right. That's right. Yeah, that's right. Come on. Okay. Yeah, so that was one of the projects that I did when I was a graduate student. We all wrote Wikipedia pages of reactions, and sort of this is one I'm proud of. So, you know, if you remember this for any other reason, Dr. B wrote it up. Let's see. So this one, yeah, right. Same process. I can't quite see I forgot what the name was. What's the name? Does it say up there? No, it's blocking it. You know what though? You don't even need the name of the reaction. These are good proof. Okay. And so right, this is the same thing, right? You get deprotonation, right? And then that thing adds into the beta position of a yeah. Oh, it's a Michael reaction. I'm sorry. You know what? Anybody here named Michael? Bummer. I always have a Michael. I had a joke, but I have to wait. Anyway, yeah, thanks. It is a Michael reaction. I'm ashamed that I didn't know that right off the bat. Anyway, see, as you can see, I think fundamentally, right? Not so much about the name reactions. Forget those. Okay. So, right. So in the Michael reaction, right, you generate this sort of enolate here that adds the beta position of an alpha beta unsaturated compound. Those alpha beta unsaturated compounds, by the way, are often called Michael acceptors. Not that clever. Anyway, so at that point, right, you can go ahead and get protonation, right, and you ultimately end up with structures that look like this. This is also going to come up for sure. These type of situations throughout the rest of MedChem. That is the end of your arrow pushing primer. What I would say to all of you would be a very intelligent idea would be to finish exam 1, swear about me for a little bit for a day or two, and then I would go through this PowerPoint extensively and really get your fundamentals down. And we should maybe talk about those. I might have one more session in which, you know, I just field questions in general about arrow pushing, so you guys are comfortable, so we can have sort of higher level discussions throughout the remainder of the course. With that, well, I'll let you out 10 minutes early. I was going to tell you get a whole bunch of more time to study, but it's not a bunch more. So go get your 1050 coffee and have a great weekend. Make sure you get a good night of sleep heading into Monday.